So the voltage clamp, basically put this like ground here in the solution, and then another electrode in the discrete axon, and then we get the difference in voltage, and then we amplify it because it's tiny, and then we put that into like this this diode that has a command potential, so that's like the target we're shooting for, and then we get the actual reading from it, and there's going to be some difference, and then we put the difference back in. We just gotta so it goes in and it set the keep the voltage in place into the command potential, and we measure the current that comes back to it. So we are controlling the voltage and measuring the current. So that's the voltage clamp. And if we're to do it the other way, where we are controlling the current and then measuring the voltage, it would be current clamp. And voltage clamping is far easier than current clamp. But anyway, so that's how we get these figures on the right. The top one is showing just like the voltage that was applied, and then these two are like what had happened. And when we see this is like what we usually get from the potassium and sodium currents. But to differentiate how the potassiums and sodium's effect, we can put a blocker. So for example, tetrodotoxin, which is from a blowfish or pufferfish, a poison, and which is blocking a sodium channel. So we are only measuring this potassium, and we see that the current like shoots up, and for sodium it like shoots down. And the reason why it's going back up for the sodium is because they have their mechanism is kind of like a positive feedback loop. So the more they work, the more they get activated, and so on and so forth. And so there's a mechanism to stop it, and it's built into the sodium channel itself. So once it reaches a certain value of current, it kind of goes back. It stopped working. But anyway, yeah. So we see that potassium increase the current, and sodium the other way. And this Hodgkin find out that the sodium works. We see that there's when the sodium solutions on the axons are like in, when there's like less sodium, like it like shoots up a little less. So 100% compared to 50% compared to like 33%, we see that 33% is the lowest. So what it means is that when the solution is, the sodium is low in solution, it spikes less, which means that sodium is responsible for the spiking, and that gives him a Nobel Prize. So going back to this, so we control the voltage to measure the current. So this is a voltage clamp, and we see that initially it kind of dips in, which means that when the negative current means the ions are flooding inward into the cell, and then like eventually the current turns into positive, which means the ions are moving out of the cell. So he gave a bunch of different voltage, depolarizing voltage, and then we see that at the beginning. If you see here, it's somewhere between like 50 and 70 here. There's where the current becomes zero, at least at the beginning, which indicates that because when I is equal to 0, that means it's a stable state, or there is in a steady state, because a steady state, when your current is non-zero, then it is unsustainable, because it's steady state means like it can stay like that for an infinite amount of time. Well, if there's a current, which means there's ion moving, whether it's in or out of the cells, it's going to either shrink or like burst, right? So I equals 0 means steady state, which means nurse equilibrium potential, somewhere between 50 and 70. So you know that equilibrium potential of ions with early transient current is 50 to 70 millivolts, which turns out to be sodium 1 later on. And they do similar things. So voltage, we control the voltage from like boop, 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 boop. So like negative 40 to 60, and then as we know, the potassium, so we're measuring for the lake current now, and then we know the potassium, which will be responsible for the later action, will be sitting at negative 80, so they need to do it to go down a little more, but if they did negative 8, they would have seen the I equal to like 0. Anyway, so there's this slide which is showing potassium and sodium current. So higher the membrane voltage, there's like, for potassium, we see that the electrical driving force is really high, and so the driving force is high, and then so is the membrane voltage. But as you go down lower into the membrane voltage, potassium's driving force is decreased. And the reason why this is staying the same, because the chemical driving force is a chemical gradient, the concentration gradient. And we're not really messing with the chemical gradient, we're messing with the electrical component, the membrane voltage, right? So that's what's changing. So same thing over here as well. This stays the same. This is only one that's changing. In fact, both the electrical driving force are same, because it's just all about the membrane voltage that they are putting in or forcing it to. And this purple is just the sum of these chemical and electrical driving force. And we see that for sodium, equilibrium potential is at 55, and potassium is not shown here, but if they try negative 80, they would have seen the flatlining. So we see that the late, they put in the IV curve, and this is potassium driven, this is sodium driven. We see the y-intercept is not exactly at 55, it's at like 35 millivolt, and the reason why it deviates from 55 millivolt as it should is because there's probably a little bit of potassium working on it. It pushes it a little to the left. Measure the independent, down, move on, how? So they're determining this conductance on a VI curve, which is just the slope, and specifically core conductance is like the slope of the line that connects between the point of interest and then like your equilibrium, Nernst equilibrium potentials, which should be in theory, it should be sitting on this like a line of membrane voltage on this x-axis, so that the current is 0, so it can be reached to like steady state and can be sustainable instead of shrinking or bursting the cells. But hey, again, this is experiment, so there's a bunch of like error involved, so it's not really sitting at the membrane voltage. But anyway, so what this experiment was about was you keep this membrane voltage at like V1 through a voltage clamp. After a certain time, you just suddenly changes the voltage into V2, and that will change the current to something else. And so what we can do, what that does is that initially at V1 we are sitting at like this value, so some I value over here, or V, and then all this. But if you change it like change the voltage abruptly, then you can measure this changes to V2 and this changes into V2, and then conductance stays the same, at least temporarily. And we can measure the I, and then we can plot a dot over here. And if you do that, we make this like linear stuff, and that allows us to capture the slope of it, which is the conductance. And the easiest way to do is just knowing the Nernst equilibrium potential over here, and they can just connect the dots and measure the slope. But then again, that they didn't really know about it, so that's why I did this like hard way to do so. And did the same thing for like for potassium basically. And for this one, there was it worked well, and because I guess it's like effective potassium is a lot stronger. So anyway, so it's like sitting at about appropriate value of negative 80 millivolt here, and then they did the same thing, and then dot, and then they measure the slope. So slope of the potassium is like that. It reaches a certain value, but for sodium, it like reaches like high, and then it comes back down. The reason being is that sodium the sodium has a positive feedback loop, so the sodium channel has a stopping mechanism inherently built in. And you can put in this like a parallel series model, parallel conductance model, where this is the resistance or slash conductance, and there's capacitance, and inside, outside, whatever. This is capacitance of the membrane, and this is the membrane voltage. Yeah, not capacitor. And there's current, or the number of ion that's moving. Yada yada yada. So moving on, moving on, moving on. So this gating particle, so this potassium channel is like it's like this pore that has a gate particle which determines the permeability. Apparently there's like 4 of them, like and then these 4 gating variables kind of determines the permeability of the channel. So we have 3 activation. Usually they have 3 activation and 1 inactivation gating variables. But so we're gonna model this by, so when each of this the gating channel, which have 4, so when 3 of the channels are open, we will know there will be 1 closed one, and there will be I should be actually x minus 1 now that I'm seeing that. X minus 1. So if there's like 4, we will wait. If there's 3 open one, then we know there should be like only 1 there. So yeah, actually I don't know. It should be more like, never mind, X is the probability. Okay, so this way, okay. So the probability of this opening is 50%, and then there's a probability that there's other stuff are closed are like 50%, right? Because 1 minus 50, and if it's 100%, then closed would be 0%. Because if everything's open, there's no possibility that anything is closed, right? So anyway, just a simple thing. So changing the number of open subunit. So if there's 4, like 4 open, I mean like out of the 4 variables, if there's like 3 open, there's going to be like there's going to be like 1, and then if there's going to be like, I don't know, like something else like 2, and there will be 2, and then there will be like, if there's only 1 is open, it's going to be like 3, and then 4, and 0, 0, and 4, so on and so forth. And then alpha x is the rate of closed subunit to open. So the probability, the rate of closing to opening, and then beta is the opening to closing. That's the rate. And then x is just the probability, or the number of the subunit. This. So we can multiply that and get dx over dt, and boom, boom, boom. So if you have 90 closed and 10 like open, and the probability or the rate of opening is 0.1, then we have like 9 openings, so it goes plus 9, and they got 9 because 9 moved from here to here to open, and then similar thing here. So 5 of them opened. So plus 5 minus 5, and then to 86, 14. Total is still the same, and can be represented as that. Pretty simple if you just try it, and then if you continue on, the open will dominate. Probably, pretty much most thing will be just open. And you can just continue. Same principle, same principle. So if you can model the alpha and betas into like to be a function of voltage. So it depends on the voltage, the rate at which opens and closes are changing. So for this one, the ion channels are activated by membrane depolarization, which in other words, when the membrane voltage goes up, a probability or the rate of opening up goes up, right? As seen the alpha here. And in that sense, as the voltage is going up, the probability or the permeability of this thing, or the probability of things that are open channels will reach 1, which means like everything is open. And we can see the beta, which is the closing of closing probability / permeability, or so the not permeability but impermeability. So that as the voltage goes up, the probability of closing is going down, or the rate of closing is going down. And it's the complete opposite. Now you notice the alpha and betas are switched, and so now the things are just like goes down as the voltage goes up. And so we call the depolarization activated for the first one, and then hyperpolarization activated for the second one. And for this one, we can see that this will be probably potassium, because that's the one that hyperpolarizes to like drop the thing, and this would be sodium.